Thank you. So maybe, can you see it now?
Yes.
Yep.
In fact, I'm gonna, right. That's a nice scribble. How do I erase that? Where's the controls? Okay, the controls are over here. I'm gonna move my whiteboard to here and clear all drawings. Okay, good. So the image that you take, whoa, okay, so let's draw something. Draw, I guess that's probably it. So the image that you take of course, X and Y, right? Pixel location X, Y.
Do you intend to have a narrow, tall blackboard?
Well, it looks fine to me.
Oh, it's narrow and tall, it looks to me.
I don't see any writing on it either. Have you written anything yet?
Yeah.
Oh, no.
Why does shit not work, huh?
Now it's even
Now
narrower.
it's narrower and taller.
It is a
There we go.
technology.
Okay.
You got it.
All right. It doesn't like my second screen
Oh,
for whatever reason. Okay, so the image that you take is composed of the following stuff. First of all, and I won't write X and Y for each one of these, but it's the bias plus the image, the time of the exposure time
Mhm.
times the dark current plus what we call a modulation function. This is also of X and Y times the number of photons that came through the system. So we'll say the photons, P of X and Y times the QE of the camera, right? So forth. Filters QE, this is all the normal imaging stuff, but it has this modulation function that we'll get to in a second. In other words, every pixel has a different gain. I could have called this G, but most people call it M for modulation.
Mhm.
So you notice that the bias is a fixed amount that you get every time you take an image. For that pixel at X and Y, you're going to get the same bias because it's just built into the electronics.
And that's regardless of exposure time.
And that's regardless of exposure time. So then there's a dark current. And of course, the longer you expose T, the more dark current you get. So the image builds up dark current at the same time. So this stuff here is the unwanted stuff that's coming from the camera itself that changes the level, the intensity of the image without any photons appearing through the telescope at all. Okay.
And the bias and the dark comes from the camera pixels firing, like kicking off electrons, while the bias comes from something that happens when they're red.
Okay, so let's go through where each one of these comes from a physical point of view. The bias, we can treat CMOS cameras. We could do this for CCDs or CMOS, but let me do it for CMOS because it's kind of the latest technology. We can visualize the sensor as a bunch of CMOS gates that are able to sense photons. And those gates then build up the charge so a photon comes in, it produces an electron hole pair. The hole is absorbed into the substrate. The electron sits on the gate, okay? And we're gonna measure that later. The act of measuring it has two parts. The act of measuring has one significant part, and that's called the bias. that has nothing to do with the number of photons that have hit that gate at all. It's just the 0 point. It's as if you have an instrument like calipers, right? And those
Mhm.
calipers, you zero them by pushing the calipers all the way until the jaws are completely closed. When you do that, your calipers aren't going to read 0 unless you adjust them to do so.
Okay.
They could read 5 microns or 10 microns or whatever. And every time, so every pixel is like a pair of calipers that you have to zero out each time, because you'll get a different and wrong answer unless you do that. It's just the 0 of the system.
Got it. Got it.
Then, because of defects mostly in the silicon gates, it's complicated, but these little tiny defects, which are inclusions of maybe other chemicals that you don't want in the silicon, they are constantly sputtering out electron hole pairs. They're creating basically electrons.
Mhm.
And those electrons are also accumulating on the gate, but at a fixed rate.
Mhm.
And that fixed rate is the dark current. So,
Okay.
and for CCDs, it used to be very, very high. For CMOS, it's very low. I mean, I've taken long darks and they don't show all of the bad characteristics that CCD cameras did. So if I expose for 0 seconds, I only pick up the bias. If I expose for 100 seconds, I pick up the bias, which is that 0 thing we were talking about. I pick up the bias plus 100 seconds of the dark current.
Gotcha.
So to calibrate an image correctly, I should take images at 0 exposure time. That'll give me the bias. And then I take an image at a longer exposure time, like let's say 100 seconds, and I get the bias plus the dark current. I can solve that equation for the dark current itself, right? So suppose I take a calibration image C,
Mhm.
and we know it's the bias plus, and we know it's 100 seconds long, so it's 100 times the dark current. So I simply take the calibration image minus the bias divided by 100, and that solves the equation for the dark.
I see.
And now I can put, so I expose for 0, I got the bias frame. I expose for 100, I can calculate what's called the dark current component of it. I can then, for any exposure at all, suppose it's 1,000 seconds, I can just scale that dark by 1,000. And I then have this whole piece that I put in square brackets that I can then get rid of my image from my image. So let me call that thing, I'll call it calibration 0, because that's really what it is. Okay, that's the thing in the square brackets. So now I take a real image of a star. I subtract, well, let me be careful. Yeah, that's not a good thing to do yet. Eh. Let me subtract the bias. I'm going to subtract something in square brackets here. I'm going to subtract the bias plus the exposure time of my image, which I'll call E, times the dark current, which maybe we'll call D sub C. So here's an image. It's an array. So I'm going to put a double underline. This is an image. So I put a double underline, meaning it's a matrix. And here is an image. So we subtract this matrix from the image, and that leaves us with a partially calibrated image. It's not fully calibrated because what we want to actually know is the photons that arrived at the camera, right? So we're not there yet, but we got part of it. So that's equal to the modulation function, which is again a function of X and Y, or I could say I and J, which is convenient, right? Times the photons that arrived. So that's really a matrix 2, right? And this multiplication is not matrix multiplication in the classical sense. This is just multiplying a number times the number of photons that arrived times a bunch of other stuff, you know, that involves the filter, the telescope, vignetting, and everything else, right? That can either be all put in the modulation function or it can be left out. So the modulation function is a complicated thing that, so let's write that down. Where's the erase again? Eraser. Erase. Oh. All right. I don't know.
Also, I suppose if we have a meeting at 11 that I should have already
well, that's a
probably
good
gone
place.
for.
A good
Maybe.
place to stop. Yeah.
But this is really helpful. I think I sort of see what this guy was doing and how I should proceed, but I will bring further questions next time for sure.
I'll make a PowerPoint about the subject in much more detail.
That would be wonderful. Thank you so much.
And
there's a
then we
good
can-
program that can help you import all of your calibration frames and stack them and combine them with your lights. It's Deep Sky Stacker. It's a free program that you can download.
Oh, Deep Sky Stacker. I might do that to check what I've been flailing around with in Python, taking medians of things and subtracting things blindly, thrashing wildly, as is my usual method for these things. But
What
this would be a
telescope
good way to it's someone from AAVSO, and I don't even know the telescope. Just I was talking about my frustration with LCO's inability to take less than 1 second images, and he was like, "Oh, I can take some images of Delta Sep," and so he sent me some, and that were low exposure time, and that's why I was just like, he was just like, "Oh, they're not calibrated, so you'll have to calibrate them," and I was like, "Okay."
Hey, I've taken 1/10 of a second exposures on LCO.
Really?
Yeah.
Yeah, for some reason
Yeah.
it was saturating everything for
Oh,
me.
well,
So
yeah, but I had to for really bright stars and it worked.
oh, that's useful to know. I might ping you later for your technique for that, but I should get to my meeting that I'm already late for. No, but thank you all so much. And I will see you next time.
All right.
Bye.
Well, I'll say that I tried the Zewo calibration frames that wouldn't even calibrate one that we had. I don't know why that was, that Rick calibrated last night or the night before. And
Yeah, I had to put in the proper.
I tried a different slice of QSI frames, just a different set, same problem. So it's